Alright then, so another video for the another search algorithm, which is all about the breadth first search. So in this case right now, let's define what is breadth first searching algorithm. So in this case, breadth first search, that is definitely a graph traversal and a search algorithm that explores all the neighboring nodes and the present depth before moving on to the nodes at the next level. So as what we have did already in our data structures and algorithm, that we were able to basically start from the level zero up until the level n. So that's how you will begin to to perform this operation, and you will be going to use a Q data structures here. Q data structures in your Q data structures, you have the front and end that is both open and your font, as well as you can insert at rear point and you can delete that font. That's how it will be it will work here then. It is somewhat helpful in finding the shortest path in an unweighted graph and for problems like finding connected components. And we will explore a graph or tree level by level, starting from the source node and visiting all its neighbors before moving on to the next level. That means to say that we can definitely expose first, we can insert all the adjacency in the queue before we will remove that element. Then we'll search the second element and we'll check the next adjacency of that particular element, and then you will begin to definitely process everything and then until you could be able to work on with those implementation. Next, there will be a steps for the breadth first search actually. So first, you have to initialize the data structure. You have to create a queue to store the nodes to be explored. So always be mindful that we are using here the queue data structure because it explores nodes in a FIFO manner. When I say FIFO manner, that is first in first out, as we have already dealt with that in our previous discussion. And that is a first in, first out order. That means to say we're having the queue data structure that we could insert that particular element in one end, and we could also delete in the other end, rather. Sorry. So right now, create a visited array as well to keep track of which nodes have been visited and avoid revisiting them. As pertains to that, it's somewhat the same with the depth first, that you cannot revisit the particular element if you were able to visit that one. So that is restricted for at least once visit in that particular element then. After, you have to include the start at the root node, mark it as visited and include it into the queue. So you have to work on that, have to insert what is that specific element, and you have to check the adjacency. Afterwards, you have to begin the BFS loop for the breadth first looping. While the queue is not empty, you have to declare a node from the font of the queue and visit the node, process it, like print its values or store it. In this matter right now, if you are not able to search yet the key element, you have to check the particular adjacency of that particular element that you are at now. Then what will be the adjacency of that? You have to insert that at the rear point, and then afterwards, if only if the adjacency of that given element in the font end right now, if you were able to expose to visit the all of those element, so that's the time that you will begin to declare the first node as well, and then you will continue the looping. Then explore as well here, explore neighbors for the node that was not for the node that was secured. Visit each of its unvisited neighbors. So after you were able to visit those, I mean the queue, this the first element, you have to check what will be the adjacency of this second element then. That is the neighbor of this one. Then you have to mark each neighbor as visited if it hasn't been visited already. So you have to in queue the neighbor into the queue to explore later. So in this case, for example, you were able to search already the first element, then there will be adjacency of that. You were able to insert that successfully in the rear end. And then afterwards, that since you were able to exhaust everything, this is the time that you will begin to queue the first element in your front end. And afterwards, you will also check remove or dequeue. Then after dequeuing, the second element will be visited. And what will be the adjacency of that? That's the time that you will also include that in your queue and then do the algorithm repeatedly. You have to work on that. Then repeat until the queue is empty. Continue the process until the queue is empty. And at this point, all reachable nodes from the start node have been visited. So that means to say that you were able to exhaust everything. If you were able to um, found the element, that's the time that you will begin to terminate the search. When the queue becomes empty or you were able to search the key element, the search terminate the search. All nodes in the connected component of the start node have been explored. So if you will be going to perform the breadth first search, you have to remove up until the it will be empty. But here then we're just focusing in searching. So if you were able to found that specific element, we just have to terminate the searching. Now we will be going to explore as well the this kind of what do you call this one? This searching in the another example. And by the way, the complexity for this. So for the time complexity, it will be the same thing with the DFS that we are having the O of V plus E, where the time complexity of the breadth first search is determined by the number of nodes or the vertices and edges that the algorithm needs to traverse. When we say the V, or that is the vertices or nodes in your graph, and your E, that is the number of edges in the graph. Since if you'll begin to define the time complexity of the V, that is O of V, and then the E, the edges, the time complexity of that one is still O of E. So since in every search we are keep on adding and adding that one, so that means to say it will be the O notation of V plus E, the vertices plus the E, the edges that you have. And lastly, the space complexity is still O of V, meaning the space complexity of the breadth first search depends on the number of vertices stored in the queue and the visited set. So that's how it work for the breadth first search, and I'll be going to illustrate to you the example in the next video. Thank you.